So we've spent some time talking about how we might count up the microstates for a given distribution. I want to illustrate this with an example. Now I have recorded the result that we got last time up here in the upper right hand corner so that we can use that as a reference. Our general approach is going to be here for applying statistics is that we first want to find distributions that will meet the criteria of our system. So in other words, find distributions that are achievable, and I'll describe what I mean by that in just a moment. The second step is that we want to evaluate the number of microstates that each one of those distributions would have. Number of microstates. And then finally we would want to determine which of those distributions has the most microstates. The one with most microstates, because that will end up being the one that is the most probable distribution of all of the ones that we can possibly achieve. Now when I say that we want to find the ones that are achievable, I want to especially note that we're going to be working with a couple of constraints. These constraints are determined by the number of molecules, so we're going to say the number of molecules in the system is fixed, but that has to be equal to the sum over all of the distribution numbers for each of the states, E sub j. We also will have a constraint that is related to the total energy, and it will be related to the sum of the energies of each of the molecules. So we have N sub j molecules that have energy E sub j, so the total contribution from those N sub j molecules will be the sum of those, and then over all of the possible molecules in the system, they will add up to the system energy. So this big E here is really the system energy, and so we're exercising that as a constraint on what our total system could be. Now, in order to illustrate this, I will tell you that molecular systems have way too many molecules and way too many energy states for us to put together an example that would be possible to get our heads wrapped around. So I'm going to purposely give you a much simpler example so that you can sort of see how it works in principle. And you'll get a chance to work this out on one of the problems. But this is, I'll just say, a much smaller and much simpler example than you will actually see in any sort of molecular system. So I'm going to index this with the index j, and I'm going to say suppose that my energy levels are actually given formulaically by j minus 1. So in other words, when j is equal to 1, 2, 3, 4, and so forth, the energy for j equals 1 is going to be 0. For j equals 2 is going to be 1, 2, 3. So you can see that our energy levels are equally spaced. This is actually, in reality, only true of a harmonic oscillator, but we're going to take it to be true here. I'm also going to assign degeneracies to these levels. And I'm not going to do that with a formula, but I'm just going to say that the lowest energy level has a degeneracy of 1. The next one has a degeneracy of 2, then 6, then let's see, 12, 24 for number 5, and so forth. So these are going to be our working degeneracies. And you'll see that what I've built into here is actually the case. And actually, let's go up to 6. And we'll say that that highest energy level has well, we can make one up. Let's just say it has 36 or 48, something like that. You'll notice that I've built into this that the energy levels, as they're going up, the degeneracy is going up even faster. And this is a fairly realistic feature to have here. Now what I want to do is characterize a system that I've specified both the number of particles and the energy. So we'll have the number of particles is equal to 5, and the energy total is going to be equal to 10. And so what I want to do is create a table that sort of characterizes each of the distributions. And we'll look at a few of the distributions. I'm not going to look at a whole bunch, but I want to look at a few just to show you what this all will look like. So on this table, I'm going to first of all give values for the degeneracy and the energy level. The lowest energy level is 0, then 1, 2, 3, 4, and we'll say 5. And the degeneracies that I'll give for these are 1, 2, 6, 12, 24, and I'm going to go ahead and make this 48. I like 48 better than 36, so 48. All right, so those are my degeneracies. Now I want to specify a set of different types of distributions. Now what goes into this? Okay, well first of all let me show you one that wouldn't work. All right, let's suppose I need to have the energies add up to 10. That's my limit. So I could have one molecule that has energy 5 and maybe one that has energy 4. Then I only have one energy unit left, so I'm going to have one that's got energy unit 1, and then the rest of the molecules, and there's 5 of them, would have to be at energy 0. So that means 0 here and 0 here. So this would represent a distribution. But is it an achievable distribution? The answer in this case is no. And the reason no is because this number is bigger than the degeneracy for the state. So I cannot actually achieve this distribution. So I need to find distributions where the number that's listed here in the row, all of these numbers are less than the number that is up in the degeneracy row. Okay? And it's true of all of these except for this first one. So this first one ruins it for all the rest. They can't be achieved. All right, so let's look at some that could be achieved. So I'll label this first one A. And let's suppose we have, in this case, we again have a molecule that has energy 5, but I know I can't do 4 and 1, so I'll put 0 that have 4, 1 that has 3, 0 that have 2, 2 that have 1, and I've used up 4 of my molecules, so I have 1 left. And now if we check, all of these numbers are lower than the numbers here in the row that contains the degeneracy. So this is a possible distribution. Okay, I'm going to introduce a couple more and then we'll do some analysis of them. So I'll introduce another one here. Let's suppose we have 1, 1, 1, 1, 1. And if you add all that up, 1 plus 2 plus 3 plus 4 is equal to 10, which is our target energy. So I can't have any more. So this will also be a legitimate distribution. Let me do one more just to seal the deal here. Let's suppose I've got 3 that have energy 2 and 1 that has energy 4. So I've got 3 times 2 is 6, plus 1 times 4 is 4, so 4 plus 6 is 10. So I don't have any more energy. I still have one more molecule, so I'm going to have to put it down here in 0 energy. So all 3 of these are achievable distributions. They match both the number of particles and the total energy. So now what I want to do is I want to use these achievable distributions and calculate the number of microstates in each. And I'm going to use this formula that's in the top right hand corner to do that. So for this one, I've got one molecule. So Nj is equal to 1 in level 1. That has a degeneracy of 1, so it's going to be 1 raised to the 1 power divided by 1 factorial. Then I have this big pi sign here means I'm going to multiply all these together, so I'm going to multiply by the number of microstates that's generated by this one. I've got a degeneracy of 2, so that means I'm going to have 2 raised to the 2 power divided by 2 factorial. Then I'm going to have 0, that will be degeneracy raised to the 0 power, which is 1, over 0 factorial, which is also 1. So anytime I have a 0 here, that's just going to give me a factor of 1. Okay, now for 1, I've got a degeneracy of 12 raised to the 1 power over 1 factorial. I've got again a factor of 1, and then I've got 1 here, so I've got 48, degeneracy of level 5, raised to the 1 power over 1 factorial. So you can see that in constructing all of this, this first factor is going to give me 1 over 1, so that's 1, times 4 over 2, that's 2, times 1, times 12 over 1, that's 12, times 48 over 1. So if I do all of that calculating, I would find that I have 1,152 different microstates that are associated with distribution A. So quite a few. There's a lot of different ways I can put these molecules in here so that I've got one with energy 0, two with energy 1, one with energy 3, and one with energy 5. And a lot of that is coming from the degeneracies of those states. All right, I'm not going to belabor the other ones quite as much, but I'll simply point out that for B, it's pretty simple because all of the populations are 1. So it's just going to be the product of the degeneracies that are shown up here in the top row. So I'll have 1 times 2 times 6 times 12 times 24, and I don't have any molecules in energy 5, so that's it. And when I get through multiplying all of that, I'll find that in fact I have 3,456 different microstates for that one. What about distribution C? Okay, well in this case I've got one molecule in the 0 level, so I'll have 1 to the 1 over 1 factorial times 1. Now I've got a 3, so I'm going to have to take this degeneracy of 6 and raise it to the 3rd power divided by 3 factorial. Then I have another factor of 1, and I have a factor of 24 raised to the 1 over 1 factorial. Now what is this thing here? Well, 6 raised to the 3rd power is going to be now divided by 3 times 2, which is 6, so it's really just going to be 6 squared, or 36. So in effect, the number of microstates here is 36 times 24, and when I do that multiplication, I'll find that in fact it's 576, if I did it right. Hopefully I did it right. So now, as we look at this, and I'll tell you there are actually many more distributions that we could generate in this system with these constraints of n equals 5 and e equals 10. But I just want to look at these few. I've got microstates of 1152, 3,456, and 576. So clearly this middle one, distribution B, has the most microstates. So in some ways I could say that it is the most probable. It's certainly the most probable of these 3 distributions. Now there may be another distribution that we haven't looked at just yet that could have more microstates, but my guess is that it's probably going to be number B. Now what is the difference between B and these other ones? Well, one of the things that characterizes distribution B is that it distributes the molecules across a lot of different energy levels. So we have a lot of different levels that have one molecule each in them. And it turns out that this is actually a pretty favorable way because it generates the most possibilities for different microstates that could arise in a situation like this. I'll also notice that in real systems, we would have an n that is something on the order of 10 to the 23rd, not 5. So in this case, we have a little bit of preference here for distribution B, 3,456. It's only about 3 times the one for distribution A. It's about 6 times the distribution, 6 times the microstates that found in distribution C, but it's not a spectacularly larger number. We're going to find that the most probable microstate when we have a lot of molecules like 10 to the 23rd is actually going to be a lot more favorable. All right, but this small example at least gives you an idea of how one might go about physically assigning molecules and determining the microstates for them. So I hope it's been instructive.